Hello everyone. We were talking about example 2.2 about moving bottlenecks. So let's keep going. So the setting here is that we have a truck using the highway for a distance L starting at location X0, right? And we said that the solution is very similar to the incident example except for the connection between states D and U that now follow a line of slope V, which is the speed of the bottleneck. So speed of the truck in this case, okay? Okay. We already talked about this, so the Q could go forward or backwards depending on the location of the demand A. Okay, this is when the speed changes gradually, so it's a gradual acceleration. We talked about that last time. Okay, so today, let's start with this special case of the previous example, which is very important because this would be a moving bottleneck, like a lane change, right? And it turns out lane changes are the ones that are responsible for the phenomenon of capacity drop that we will talk probably next week. All right, so in the context of a lane change, let's say this is the time-space diagram of the target lane, okay? So you have a lane change that probably is going to start right here, right, at the beginning. So that's when the lane changer hops in the target lane and start accelerating. Now the reason he accelerates is because he changed lanes coming from a lane that was going slower. Actually the speed V1 right here could be the speed of the origin lane, right? So when you change lanes, you kind of have the same speed of your origin lane and then you speed up, okay? And you speed up like this in 3 segments here, just for illustration. So these are the 3 speeds, and you're going to generate the states U1, U3 very similarly to the other one. The key point here is that now state D, the downstream state, is the state O with no flow, and we call this a void. So the D is the voids, and void means emptiness, right? So the lane change or moving bottleneck will produce this void in front of it where you wouldn't see any vehicles, right? Because we're focusing on the target lane only. So there won't be any vehicles in the target lane, so you would see just empty space. And it turns out that this empty space will propagate downstream indefinitely, like that, unless people cut in, right? Somewhere downstream. Because this is the free flow speed, U, right there. So this one. Oh, it's supposed to be U. Yeah, it looks the same as my capital U's though. Anyway, so this is a free flow speed U. So this void would stay there kind of forever, unless, people change lanes into the void, which we always do, right? Typically downstream of a truck, things are much easier to change lanes into. And then, but if there's a congestion downstream, then this void would disappear, right? If you reach a queue or something like that. But these are really persistent. And the problem happens when these voids happen at the location of the bottleneck, meaning that downstream there's not going to be another bottleneck, so these things would kind of prevail. All right, now, an important point here is that if you drew a trajectory such as the one drawn here in black, you would see that it is a translation of the leader trajectory translated by the wave speed W. So all these are, as usual, lines with slope W. And these are the shocks, right? And as usual, it's, wherever A is, then these are all the 3 shocks that you would see here, 1, 2, 3. So if you drew a trajectory like this one, so in state A, you're going at free flow, so that's free flow. But in state U1, right here in orange, the speed is the speed V1, right? As always, right? We draw a line and to the state, and the slope of that line is the speed. But now it turns out that the speed is the same as the speed of the moving bottleneck. And that didn't happen here, right? Because here we have two lanes. We're focusing on all lanes at the same time, right? Because this is our fundamental diagram, if you will, of all lanes. And state D is just, again, the number of blocked lanes, right? So state D is a consequence of how many lanes you blocked. So the more lanes you block, obviously state D would be closer to the origin. Okay, but in our case, right here, it's as if we blocked all the lanes or if we just focus on one lane. And that turns out to have the effect that the trajectories of all the vehicles inside the congested area are a translation of the leader trajectory. Okay, so this segment right here is exactly equal to this one, just translated along the waves of slope W. Okay, now that is kind of enlightening when we talk about car following models. And in particular, Newell's car following model is exactly that. So in free flow, Newell's model says you can go at your free flow speed, right? No problems in free flow. But in congestion, you're gonna use the same trajectory of the leader, just shift it a little bit by the wave. Okay? So let's keep that in mind until chapter 4, I guess. Okay. So this is the same case of a lane change, but here the speed change is gradual. So it's not in piecewise steps. It's kind of following probably a linear acceleration model. So you have kind of a continuum of traffic states, U1 to UN, if you will. But they all go at the same speed, negative W always, right? So now you can think of each line as having its own state, U. And it's a continuum, right? So, and again, acceleration, the speed of the lane changer goes from here, probably started near you here, and then went all the way following this arrow, right? And ended up somewhere here or here. Okay? So that's why we said that this is a U of t comma x. It depends on where you are. Okay, but what we said is still true, is that if you want to draw a trajectory, what you're going to do, so you're going to start here, and state A is always U, but here, what you're going to do is follow the leader. Now, at this point, what speed should you have? According to our previous discussion, you're going to go up with the wave speed and see what the speed of the leader is right here. Let's call it V1, which means that your trajectory here would have speed of V1 as well. Right? So if you keep drawing these waves of slope W again, well, negative W, the speed here equals the speed here, right? Which is consistent with the idea of characteristics, right? We know that from the transport equation along characteristics, the density is constant. And if it's one lane, that implies also that the speed is constant. So all the vehicles crossing the street right here, they all going to have the same speed. Whatever the speed is here, let me call it just V. The speed of vehicles crossing this characteristic is always going to be V, according to the model. Okay, all right. Let's focus on the next example of a traffic light. So classic kinematic wave example. All right, so we have a single intersection located right here. And then we have the signal timing. So during this time it's green and red, etc. Right? Okay, so this is very similar to the incident example. So the solution, we're gonna go kind of faster now. But you see that is the same logic, right? So at each time or point that something happens, you try to figure out what the corresponding Riemann problem is. Right? So here we have kind of all the Riemann problems. You want to see case 1 or 2, and then you act accordingly, right? So, for example, starting here, when it first turns red, it's like an incident, exactly like an incident, right? So, an incident, we already know we have a shock that creates the Q. Now, the Q is going to be called state R for red, okay? So, the red is red, obviously. And then downstream of the traffic light is the downstream state of the bottleneck, which in this case is state O, okay? Because you're blocking all lanes. All right, and then as soon as it turns green right here, then it's like removing the incident. So we know already the solution is the wave speed, like that, and then we have the capacity state here and there, right? So these are people exiting the intersection at capacity, which is the tip of the triangle. All right, and then when the second second cycle, right, comes in. So in this particular case, not everyone had exited, right? Like this vehicle right here, let me try it, got stuck for another cycle. So he's going to have to wait, go parallel, and then he will be able to exit, right? Okay, so what happens here, it's a similar Riemann problem to all the others. It's just it's going to be, at first, we're going to have a transition between C and R. You see, they are connected right here. And so, let me try to zoom in here real quick. So what happens is, oops, what am I doing? There you go. That was a weird trajectory. What happens here is that, so the last vehicle is this one, right? So when you go up, you're going to hit the next Q in red, right? So at this point, your Riemann problem will see, so right here, you would see the connection between state C and R, right? And now between C and R, we have, wait, I think I'm not showing the whole screen. Between C and R, they're connected by the congested wave speed. They're on the same line. So, okay, I'm trying to zoom out here, but it doesn't let me. So the transition between C and R is going to be a straight line. Absolute W as usual. Okay, this is... Okay. I think I got it now. Right, that should be good, I think. Okay. So that's the situation with the second cycle here. All right, and then after C and R split at this point, then the solution is the same for all the cycles, right? So we're going to have this shock between, again, the demand A and the red, etc., etc., etc. Okay? And here at the last cycle here, we said what would be the green necessary so that everyone makes it through the intersection, right? And that was a simple question because, again, this is the last vehicle, so we just have him exit. And after this point, you can put the next red, right? That would be kind of an actuated signal or traffic responsive. All right, what you're seeing here is a case of an oversaturated condition, which means that from cycle to cycle, the queue keeps building. All right, an unsaturated case is one where at each cycle you discharge the whole queue, so nobody's waiting for more than one cycle. Okay? So undersaturated, it's a lot easier to analyze, right? It's just you do it once and then you kind of copy paste. But here you see like an accumulation, right? The first cycle you have this excess queue, the second one, this one, and that's going to grow from cycle to cycle, right? And actually, if you see the length of the queue or the extent of congestion, you see these points are going upstream. So eventually, it might reach the upstream entrance of that road segment. And that's what we call spillback, right? Which unfortunately is very common in congested cities. And so it's when the queue, right, goes over to the entrance of that road segment. And typically there's going to be another intersection there, so you won't be able to discharge from those intersections. Very good. Now, let me show you some real trajectories about traffic lights, where you can clearly see these triangles that arise. So these are examples of the ngSim data collection effort. So it's called ngSim. It was very popular, still used a lot. It's kind of the main effort that the FHWA performed to collect actual trajectory data using video. So yeah, you did one for the homework, right? And there's 2 or 3 more data sets. This is one right here in Peachtree Street, or West Peachtree, one of the Peach Streets anyway. Okay, so here you kind of see very clearly one such triangle. So this is traffic state R, this would be traffic state 0, right? There's nobody. Well, there's one right here, but it's a turning movement, I guess. So that's why we have these triangles, because, and you see now the reason, right? Because you see the actual trajectories, is because people are coming in, right? And it's the back of the queue. And that's what we call a shock, right? And that's why we see these triangles. Now, we don't see the very tip of these triangles, right? Because there's no more cars coming here. If I had another car here, probably I would have completed the tip, right? But there's no one else coming. So that's why. Same thing here. Now, these don't look like triangles. Well, this does. But again, you don't see it because there's no more cars coming here. This one looks like actually a rectangle, right? So it's like this is always the wave speed. Now this guy, since they're parallel, is always the wave speed. Well, it is the wave speed. So what it's telling you is that the traffic state of this segment right there is capacity, right? It's a discharge from the previous intersection right here. So let me erase it for clarity. And actually, let me zoom in. This is interesting, right? So here we have one intersection, and here we have another one, and here's a third one, right? So all these are, okay. So this is the green for the most upstream intersection, and it's discharging at capacity. Oops. Because, how do I know it's capacity? because when it comes to the red, you see that this is almost equal to the wave speed. Okay? Well, it's a little less. So this would be a little less than capacity. All right? Okay. And notice how just by looking at the picture, you can kind of figure out where the reds and greens are. Right, so obviously these are reds. Let me just color the reds. When you see car stopped, it means that there's a red face, right? So this is actually a method to try to compute the traffic lights settings if you don't know them, if you just know the trajectories. Right, that would be a pretty good approximation of what the timing is on all these, right? And all the rest are going to be greens, obviously, right? Such as in the figure above. All right, so that's real data. It's always good to check the real data and compare it to our examples like that. Okay, actually, let me show you more real data. This is very recent. This data has been collected using drones in Greece. Let me see if I can zoom in around. No, it doesn't that way. Oh, damn it. Yeah, I did. I don't know how to get rid of that now. Okay, so you kind of see the same patterns. So I wasn't able to zoom in, guys. I'm sorry. Technology beat me. That's fine. But you can still see the triangles, right? For example, well, I don't know if I'll be able to right now. Yeah, I guess that's a good one, right? Can I change the color? Yeah, that's a good one. Well, you see, there's a lot of congestion. You see these. So here we have like 1, 2, and 3 intersections in a row, right? And here you see the end of the red there, right? Spilling back all the way 2 intersections. Here you see another spill back, etc. So the natural question is, how can we time these in a better way, right? So we'll be discussing that in the future. Okay, I think I had another one, but I don't seem to be able to. Yeah, that's the other one. I think this is a zoom in version of the same data, where it shows you clearly these triangles and all the good stuff. All right. Let's go back to our examples. Now, let me do. All right. Let's do these examples. So we're going to have a lane drop, and then we're going to have an incident just downstream of the lane drop, right? So this would be the solution. So let's go little by little. All right, so we have the lane drop right here. So at this location, we have 2 lanes going into 1. Okay, we're going to start with an empty freeway. So with traffic state O right here and O right there. Okay, so all this is empty and equal to O, just for a change, right? We could start with A, but let's start empty. Okay, so at t equals 0, we're going to have the first vehicle. So that's your first vehicle. First vehicle in the morning. Okay, and behind him, you're going to have everybody at traffic state A right here. Okay, it's going to be A all the way here. Now, when this first vehicle hits the lane drop, that's going to have the effect of a incident, right? Not everybody can make it through. Why? Because this right here is the fundamental diagram for the one lane segment. And the big triangle is for the two lane segment. Two lane. Right? So the capacity, notice, is 2 times Q, right? And here is just Q. Now the traffic state, this one is C1. We're going to call the corresponding to this two lane segment to C2. Okay, so that's the bottleneck. The one, I'm going to erase it because it made it worse. So that's C1 and C2. And that's your bottleneck. So here, the incident solution, you have a shock wave, right? The slope right here is the shock wave between A and C2. So this one, right? Because C2 is the congested state that corresponds to a flow of Q of one lane, right? But in the two lane segment. Okay? So again, since we have one lane downstream, that's the bottleneck. So that's the capacity of the bottleneck is Q. And it generates two traffic states, C1 in the one lane segment and C2 in the two lane segment. All right, so upstream you have this Q in C2, and downstream is C1. The connection between the two turns out to be they're at the same level, right? So it is as if there was a straight line interface there between C1 and C2. All right, to get a better intuition for that, you can think in the following way. Right, so we know the fundamental diagrams are different upstream and downstream of the lane drop, right? So in these cases, we reason as follows. What is the same in both segments is the flow. So the flow that crosses both segments is the same in either segments. What we're saying here is that Q, you would see the flow Q in both these segments. But the flow Q in the one lane segment is in free flow, right? Because you passed the bottleneck already. So that's going to be C1 right there. And the other one is going to be C2 in congestion and in the two lane segment. Okay? So when you cross that transition, you keep going at the same flow, all right? But you're going to have different speeds. So in C1, you're going to go in free flow, right? And in C2, the speed would be this one. All right? But the location where you speed up is always the same, and it's the lane drop. So that's when you pass the bottleneck. All right? Okay, let's keep going now. So at some time, we have the incident. All right, so this incident happens right here. And it blocks maybe a portion of a lane such that the flow that can actually go is mu. So this is your bottleneck capacity of the incident, and this guy is going to generate these two traffic states, D and, well, three actually, right? D, we're going to have U1 right here and U2 right there. Okay? So this is an incident like any other. So first there's a shock between C1 and U1. Okay, and the slope of that shock is just negative W, the same as here. Right, so that's why we have this line. Downstream of the incident, we have state downstream right here. Right, so your normal incident. The only difference here is that here the shock is actually a wave. Okay. All right, and then the incident is removed, and we already know how that works, right? So we have these lines of slope U, and then the capacity state. Now, it's the capacity state of the one lane segment, right? So that's why it's going to be C1 right here, right? So basically just your typical incident solution, right? Now, the interesting part comes here when the Q of the incident reaches the lane drop. And then we reason in the same way. The flow that crosses here has to be the same and is equal to mu. Okay? So you only need to know whether you're in free flow or congestion. Well, they're both congested here, right? So you're going to have U1 and then U2 in the two-lane segment. And then again, the transition is flat like that because they're at the same level of flow. Okay? And this is what's different about this problem is that since we have different fundamental diagrams, right, we're kind of stitching together the solution of two homogeneous problems before and after the raindrop. But the way to stitch them is by this argument that the flow crossing it is the same for both. Okay, so that explains U1 and U2, and again the transition is flat. Okay, so at this point these two will cross, and then we figure out that here we have the shock between A and U2, which is steeper than the other shock, right? And therefore it goes a little faster, and eventually, spills back to the entrance here. All right, and when the incident is removed, we have this wave. Okay. Okay, I didn't say why this keeps the same slope, but you can see that it's the transition between C2 and U2, which are in the same line, right? So they keep the same slope. All right, and same thing happens here when C1 reaches over or spills back to the two-lane segment. You have a transition between C1 and C2, which is flat, right? So we can continue this line, and then between U2 and C2, which are connected by the line of slope W. So that's the transition. All right, and finally here they cross, and therefore there's another shock between A and the state here, which is C2. So from A to C2, you're going to have the same shock as we had here. All right, and there you have it. That's the solution. It's a little more complicated than the others. It's like putting two solutions together. And the main point again is how do you go about going from the one lane segment to the two lane segment. All right. So this is the case when it's a very congested case, right? When the demand going up here, so state A going up, exceeds the capacity of the one lane segment. Right, so you're always going to have a Q, like in here, right? You have a Q and then that's it. Here we have the case where QA is less than Q. So in the absence of an incident, you wouldn't generate any congestion, okay? So I'm going to leave this up to you. It's a little simpler, right? So before the incident happens, everything is state A. So and then you're going to see that the Q doesn't spill back all the way to the entrance, but eventually it recedes and goes up. Okay, Now, the reason it goes up is simply because the shock now between A and C2 is positive. Okay, that's supposed to be A right there, and that's C2. So it's positive, so it goes up. And eventually reaching here, and once you go to the one length segment, there's going to be a transition between C2, well, this is between C2 and C1. Here is going to be between C1, right, because C1 is all over here. So C1 and A, right, which happens at free flow. Okay, so please work it out on your own. And finally, when the demand equals the capacity, so state A is right here, then nothing happens at the beginning because you're right at the capacity, but eventually here you're going to have this build back, but curiously it's going to stay here forever because the transition between A and C2 is flat. Therefore this line is flat, so parallel to this one. So this is going to be C2 forever and ever. Of course, until the demand drops. Okay? Very good. This is one with on-ramp with priority. Yeah. So let's talk about on-ramps right now. So this is a prelude to our next section, which is how to deal with on-ramps. The problem with on-ramps is that you need to specify the priority, how people negotiate the on-ramp. Okay, and typically we use the zipper rule. It's one from the on-ramp, one from the shoulder lane, right? So we're going to see all those models in the next chapter. In this example, we're going to assume that the priority is given to the on-ramp, just to be able to see how these work. Okay, and it's very unrealistic, I know, but it's going to help visualize things on the on-ramp. All right, so we have our freeway right here and the on-ramp. The flow of the on-ramp is QR, as usual, state A for the freeway. All right, now this is going to be the flow pattern or the demand pattern for the on-ramp. It's going to have two levels, Q0 or Q1. Okay, Q0 is a very low flow such that the sum of the freeway flow plus the on-ramp flow Q0 is less than the capacity of the freeway, so you should have no congestion there. Excuse me, but Q1 is high enough such that the sum of all flows exceeds the total capacity, right? And then you're going to have congestion. Okay. Now, this is state A in the fundamental diagram, all right? So the key here is that the effect that on-ramps have on traffic, and assuming that they have priority, is that they would limit the capacity of the freeway to the freeway traffic. So if normally they had capacity C, or NQ actually, which is right here, if you have an on-ramp, it means that the available capacity actually is going to be NQ minus either Q0 or Q1, right? And that's the key of this problem, is that you can measure the effect of the on-ramp in the freeway by subtracting to the total capacity the flow from the on-ramp. And that's going to generate these 2 points, U0 and U1. And those are kind of key here. And that's the situation. So let's not worry about this as yet. Okay. So given that, this is very much like a traffic signal problem, if you see the solution, right? So before this time, there's no problem. Everybody's able to flow. Okay. At this time is when Q1 kicks in, right? So these times are coincide. So at this time, Q1 kicks in. So that's gonna subtract capacity from the freeway. And you're gonna have state U1 right there. So in red is U1. Yeah, I can't even see it, I know. But yeah, let me use colors then. So that's U1. It's right here, big red. And U0 is in orange. So it's right there, okay? And that's the situation. It's pretty much like a traffic light. But instead of switching from red to green, it's from U1 to U0. Okay? So please take a moment to understand the logic here. And again, it's just like the traffic lights. All right? So we can draw a trajectory such as in here, right? As usual, right? In free flow, you go at speed U. Here, speed V1, speed V0, right? That's V1, and that's V0. And here it's state capacity, right? Which is U. Now, notice slight difference. So this is the location of the on-ramp, right? So here we're showing the traffic state on the freeway only. So in this portion. Okay? And here it's also from the freeway, but you need to remember that it also has vehicles from the on-ramp. Okay? So in this segment, so traffic state C contains both type of vehicles. But upstream, it's only vehicles from the freeway, which it's is the first time we see such thing. Very good. And with that, I will see you guys tomorrow.